Inside every proton in your body, a rule of physics makes something impossible happen. You can smash that proton with the most powerful machines on Earth. You can pour in more energy than a bolt of lightning. You will still never pull out a single quark alone. Try to rip one free and the universe fights back, building a brand new particle out of raw energy in an instant. We're about to break down the strangest rule in physics. It is the law that keeps the building blocks of matter locked together forever. You will see quarks vanish into sprays of particles, a force that pulls harder the farther it stretches, and a hidden battlefield hotter than the center of a star. If your brain just short-circuited a little, that means it is working. Hit like, subscribe, and get ready. The rule of confinement starts now. Zoom into your hand right now, past the skin, past the cells, past the atoms themselves, all the way down to the center of a single atom. There, inside the nucleus, sits a proton. Split that proton open, if such a thing were possible, and you would find 3 tiny points of matter called quarks. Quarks are the smallest pieces of matter scientists have ever detected. Smaller than atoms, smaller than protons, smaller than anything you could picture with your eyes, even with the strongest microscope ever built. Physicists first proposed quarks in 1964. The idea sounded almost like a joke. Matter built from smaller pieces with names like up and down, top and bottom, strange and charm. Scientists needed a way to explain patterns showing up in particle collisions, patterns that only made sense if something smaller was hiding inside protons and neutrons. Years of experiments later, those hidden pieces turned out to be real. Here is where the story gets strange. You cannot go to a store and buy a single quark. You cannot capture one in a jar. Every quark that has ever been detected showed up bound to at least one other quark, never alone, never isolated, never free. Scientists have spent decades trying to break that pattern, spending enough energy to power a small city, all aimed at a particle smaller than a trillionth of the width of a human hair. Every single time, the quark refuses to leave its partners. Picture a marble small enough to fit inside a marble that is small enough to fit inside a period at the end of this sentence, over and over, shrinking each time. Even at that scale, you still have not reached a quark. 6 types of quarks exist, but only 2 show up in ordinary matter, the up quark and the down quark. Combine 2 up quarks and 1 down quark, and you get a proton. Combine 2 down quarks and 1 up quark, and you get a neutron. Every atom in your body, every atom in this planet, and every atom in every star you can see at night depends on these 2 tiny particles locking together in specific patterns. Scientists call the force holding quarks together the strong force, and the name fits well. It ranks as the strongest force known in the universe, stronger than gravity, stronger than electricity and magnetism combined. Yet this force behaves like nothing else in physics. Most forces weaken the farther apart 2 objects move. Pull a magnet away from a refrigerator, and the pull fades fast. The strong force flips that pattern completely, growing stronger instead of weaker the farther 2 quarks travel apart. A rule exists inside every proton and neutron, a rule so strict that no exception has ever been found. That rule says quarks are forbidden from existing alone. Scientists gave this rule a name: confinement. It sounds simple on the surface, yet it hides a mystery physicists have chased for decades. Confinement forces quarks to stay locked together no matter how much energy gets thrown at them, and nobody fully understands why the universe enforces this rule so absolutely. You are about to see what happens when scientists try to break that rule anyway, and why every single attempt has ended the exact same way. Every year, physicists around the world fire particles at each other with more force than a bullet train slamming into a wall. Machines called particle accelerators push protons to nearly the speed of light, then smash them together, hoping something new falls out. Cameras the size of apartment buildings record every fragment. Supercomputers sort through more data than every video ever uploaded to the internet. Through decades of this, across thousands of experiments, one particle has never once shown up by itself. A single, isolated quark. Think about how strange that is. Scientists have photographed black holes 8 billion light-years away. They have detected ripples in space and time caused by 2 black holes colliding over 1 billion years ago. Yet the interior of an ordinary proton sitting inside the pencil on your desk still hides 3 quarks that refuse to be caught alone. Every attempt follows the same pattern. Slam 2 protons together with enough energy, and the quarks inside try to fly apart. For a fraction of a second, it looks like victory might be close. Then, before a single quark can escape, new particles appear out of nowhere, particles built from pure energy, and those particles swap partners with the escaping quark. The lone quark scientists were chasing disappears, replaced by a fresh cluster of bound particles. This happens every single time, across every experiment ever run, in every particle laboratory on the planet. A useful comparison helps here. Imagine trying to isolate one end of a magnet. Snap a bar magnet in half, hoping to separate the North Pole from the South Pole. Instead of 2 separate poles, you get 2 brand new magnets, each with its own north and south. Quarks behave in a similar way, though the mechanism underneath runs far deeper than magnetism. Try to pull a quark free, and the universe manufactures a replacement partner out of raw energy before the quark can ever stand alone. Scientists call this behavior confinement, and it ranks among the strangest confirmed rules in all of physics. Confinement does not weaken with better technology, and it does not bend for higher energy. The Large Hadron Collider near Geneva, Switzerland, the most powerful particle accelerator ever built, smashes protons together with roughly 6 times more energy than any machine built before it. Even that machine, capable of recreating conditions close to the first instant after the universe began, has never produced one lone quark drifting free. A 15-year-old asking why might get the same answer a Nobel Prize-winning physicist would give. Scientists understand the mathematics behind confinement well enough to predict it happens, but the deeper reason the universe demands it remains unsolved. That gap remains one of the biggest unsolved mysteries in modern physics, worth an actual cash prize to whoever solves it, a detail explained later in this story. For now, remember this fact. Every proton you will ever touch, every neutron buried in every atom around you, holds 3 quarks locked in an unbreakable partnership. Something invisible ties them together with a grip that has never once failed across thousands of experiments. Every laboratory that has ever tested this rule, from small university setups to massive international facilities costing billions of dollars, has recorded the exact same outcome without a single confirmed exception anywhere on record. That something has a name, and it might be the strangest particle in the entire universe. Picture a proton as a tiny sealed bag. Inside that bag float 3 quarks, bouncing and vibrating, never touching the walls, never once slipping through. Physicists actually use this picture as a working model, calling it the bag model of the proton, a genuine tool used at research labs to run real calculations about how quarks behave inside protons and neutrons, rather than a poetic image invented for this video. Here is the twist that makes this bag stranger than any container you have ever seen. Ordinary bags hold their shape because the material of the bag pushes back against whatever is inside. A proton works in reverse. The empty space around the quarks pushes inward with tremendous pressure, squeezing the quarks toward the center, while the quarks themselves push outward, resisting that squeeze. The proton exists in a constant tug-of-war between these 2 forces, locked in perfect balance. The pressure squeezing inward on a quark is difficult to picture, so try this comparison. Scientists measured the pressure inside a proton at somewhere near 100 decillion pascals, a number so large it has almost no everyday comparison. Take the pressure at the crushing center of a neutron star, one of the densest objects known in the universe, and the pressure inside a proton still outmatches it. That pressure exists inside every proton in your fingertip right now, held in perfect balance, keeping 3 quarks locked in place. Zoom into the bag itself and the quarks are never sitting still. They move at speeds close to the speed of light, constantly changing position, bouncing off the invisible walls of confinement, held inside a space smaller than a trillionth of a meter across. A proton measures roughly 100,000 times smaller than the atom that contains it. Shrink the entire planet Earth down to the size of a marble, and the ratio between that marble and the Earth roughly matches the ratio between a proton and the atom holding it. The 3 quarks inside a proton carry different identities. 2 are up quarks, and one is a down quark, each carrying a property called color charge, something covered in detail soon. These quarks constantly trade particles back and forth between each other, particles called gluons, in a non-stop exchange happening trillions of times every second. That exchange acts as the actual glue holding the bag together. Remove it, even for an instant, and the proton would stop existing entirely. Here is a detail that surprises most people learning this for the first time. The 3 quarks inside a proton barely weigh anything on their own. Add up the mass of one up quark, and one down quark, and the total comes out to less than 2% of the proton's actual mass. The other 98% comes from somewhere else entirely, from the raw energy of that constant motion and exchange happening inside the bag. Nearly everything you weigh on a bathroom scale traces back to energy in motion, not to the tiny particles themselves. That detail alone rewrites what most people think mass actually is, and it becomes the central mystery driving much of what comes later in this story. For now, the bag stays sealed, the pressure stays locked, and the quarks stay trapped, held together by something that never once lets go. Every proton depends on a particle so strange that physicists needed an entirely new kind of force just to explain it. That particle is called the gluon, and the name gives away its job immediately. Gluons act like the glue of the universe, binding quarks together with a grip that has never once failed in any experiment ever recorded. Gluons belong to a family of particles called force carriers. Light itself is carried by a force carrier particle called a photon, the particle responsible for electricity, magnetism, and every color you have ever seen. Gluons work in a similar way, except instead of carrying electromagnetism, they carry the strong force, the force responsible for confinement. Here is where gluons break every pattern photons follow. A photon carries no charge of its own. It carries the electromagnetic force between charged particles without being charged itself, like a mail carrier delivering letters without being able to open any of them. Gluons work differently. A gluon carries color charge itself, the same property carried by quarks. That single difference changes everything about how the strong force behaves. Picture 2 magnets connected by a photon acting like a string, carrying the pull between them without being magnetic itself. Now imagine that same string is somehow magnetic too, attracting and repelling other strings around it, tangling with them, multiplying the pull the farther the magnets move apart. That second picture gets much closer to how gluons behave. Because gluons carry color charge, they interact constantly with each other, creating a tangled, self-reinforcing web of force that grows stronger the more it gets stretched. Inside a single proton, gluons trade back and forth between quarks an estimated 10 septillion times every second, a number so large that writing it out looks like a typo. 10, followed by 24 zeros. Every single one of those exchanges keeps the proton stitched together for another impossibly short instant, only to repeat again immediately after. Gluons carry no mass of their own, similar to photons, yet they carry almost the entire weight of the proton anyway. That fact sounds contradictory at first, but the resolution comes down to energy. Gluons move at the speed of light, constantly created and destroyed in bursts of pure energy, and that energy converts into the mass you feel every time you step onto a scale. A massless particle, zipping around at the fastest speed allowed in the universe, ends up responsible for nearly all the weight of ordinary matter. Scientists cannot observe a single gluon directly, the same way they cannot observe a single quark directly. Gluons obey confinement just as strictly as quarks do, trapped inside particles, never once caught travelling alone through open space. Every attempt to isolate one has ended the same way every attempt to isolate a quark has ended. New particles appear out of nowhere, and the gluon vanishes back into the crowd. A question worth sitting with. Something built almost entirely from massless, invisible particles ends up weighing an enormous amount, and that puzzle drives one of the strangest discoveries in modern physics. Scientists spent years chasing that puzzle before finding a satisfying answer, and the chase forced them to rethink what mass actually means at the smallest scales of reality. The answer starts with a property even stranger than mass itself, a property called color. Quarks carry a property physicists named color charge, and the name causes more confusion than almost anything else in particle physics. This property has nothing to do with light, nothing to do with anything your eyes could ever detect. Scientists borrowed the word colour because it created a useful pattern for describing something otherwise invisible and abstract. Here is how the pattern works. Every quark carries one of 3 colour charges named red, green, or blue. Every antiquark, the antimatter partner of a quark, carries an opposite version called anti-red, anti-green, or anti-blue. These names are labels chosen because mixing red, green, and blue light together produces white light, and that mixing pattern matches a rule quarks are forced to follow. The rule is simple to state and impossible to break. Every particle made from quarks must be colourless overall. A proton contains 3 quarks, 1 red, 1 green, and 1 blue, and those 3 colours combine the same way red, green, and blue light combine on a screen, cancelling out into colourless white. Swap any quark for a different colour, and the combination stops working immediately. The particle becomes unstable, and it cannot exist in nature. This single rule explains why quarks always show up in specific groups. 3 quarks, 1 of each colour, forms a colourless combination called a baryon, the family that includes protons and neutrons. A quark paired with an antiquark of the matching anticolour, red with anti-red for example, also produces a colourless combination called a meson. Every particle built from quarks, without exception, has followed this colourless rule since the moment physicists first confirmed it decades ago. Think of colour charge like a lock that only certain combinations can open. A proton's 3 quarks act like 3 puzzle pieces that only click into a stable shape when their colours combine into colourless. Pull one piece away, and the puzzle breaks apart instantly. But the universe refuses to let a broken puzzle exist for even a fraction of a second. New pieces appear immediately, snapping into place, restoring the colourless rule before anything coloured can escape into open space. Gluons enter this picture in a way that multiplies the complexity fast. Each gluon carries both a colour and an anticolour at once, for example, red paired with anti-green. When a quark absorbs or emits a gluon, its colour charge changes instantly. A red quark that emits a red anti-green gluon becomes a green quark in the same instant. This constant colour swapping happens trillions of times every second inside a single proton, an endless shuffle that never stops, never pauses, and never once produces a particle that breaks the colourless rule. Physicists sometimes compare colour charge to a 3-way version of electric charge, since electric charge only comes in positive and negative, while colour charge comes in 3 types plus their 3 opposites. The comparison only goes so far since electric charges of the same sign repel each other and fade with distance, while colour charge behaves nothing like that. Ordinary charge stays simple enough to teach in an introductory science class, while colour charge requires an entirely different branch of mathematics just to track how it shuffles between particles trillions of times every second. The next chapter reveals exactly how strange that difference becomes when scientists actually try to pull 2 coloured particles apart. Search every laboratory on Earth, every detector built to catch particles flying out of a collision, and one pattern shows up without a single exception. Every particle ever detected across every experiment ever run comes out colourless, every time, without exception. This rule carries a name inside physics, colour confinement, a stricter version of the general confinement rule covered earlier. Where confinement says quarks cannot exist alone, colour confinement explains the deeper reason why. Quarks carry colour charge, and nature refuses to allow a particle with leftover colour charge to exist freely in the universe. Every combination of particles that reaches your detector must add up to colourless, no matter how the collision happened or how much energy went into it. A useful comparison helps here. Think about a jigsaw puzzle that only forms a complete picture when every colour cancels out perfectly, like mixing paint until it turns a neutral grey. Toss in stray puzzle pieces, extra colours that do not belong, and the picture refuses to finish. The universe treats coloured particles the exact same way, refusing to let an unfinished coloured combination exist on its own for longer than an instant too small to measure. Physicists have tested this rule to extremes that most ordinary people cannot easily picture. The Large Hadron Collider smashes protons together at nearly the speed of light. unleashing energy equivalent to roughly 2 flying mosquitoes, concentrated into a space smaller than an atom. That collision briefly rips quarks apart from their partners, flinging them outward at incredible speed. Every single time, before those quarks can travel even the width of a proton, new quarks and antiquarks burst into existence from pure energy, instantly rebuilding colourless combinations around the escaping quark. Detectors never see a lone coloured particle. They see sprays of colourless particles dozens at a time racing outward together. This rule extends beyond ordinary protons and neutrons too. Exotic particles exist, ones built from 4 or 5 quarks instead of the usual 2 or 3, called tetraquarks and pentaquarks. Even these rare, unusual combinations follow the exact same colourless rule without a single confirmed exception. Nature appears to enforce this rule as an absolute law, holding steady across every particle physicists have ever measured. Here is the detail that keeps physicists up at night. Nobody has proven mathematically why this rule must be true. Scientists can calculate that it happens, using powerful supercomputers and decades of accumulated data, and every prediction matches every experiment perfectly. What remains unsolved is a rigorous mathematical proof explaining why the universe enforces this rule so completely. A gap significant enough that an actual prize fund offered $1 million to anyone who could close it, a detail explained soon. For now, hold on to this picture. Every proton, every neutron, every strange 4 and 5 quark particle ever detected follows the same unbroken rule. Colours must cancel to nothing before a particle is allowed to exist freely. Thousands of collisions happen inside particle accelerators every single second, and every single one of those collisions, without exception, produces only colourless results, a consistency that few other rules in science can claim. Somewhere inside that rule hides the reason quarks can never walk alone, and the next chapter shows exactly what happens the instant someone tries to force one too. Imagine grabbing a quark with an impossibly small pair of tweezers and pulling it directly away from the other 2 quarks trapped inside a proton. For the first fraction of a second, almost nothing resists you. The pull feels light, almost gentle, like tugging a loose thread. That feeling does not last long. The invisible force connecting 2 quarks behaves nothing at all like gravity or magnetism. Pull a magnet away from a refrigerator, and the pull weakens fast, fading to nothing within a few inches. Pull a quark away from its partners, and the opposite happens. The force barely changes at first, then begins climbing, stretching tighter the farther the quark travels, exactly like pulling apart a thick rubber band. Physicists call the connection between separating quarks a flux tube, a narrow string-like channel of pure force stretching between them, carried entirely by gluons. A magnetic field spreads outward in every direction and fades with distance. A flux tube stays narrow and concentrated, refusing to spread out no matter how far the quark travels. That concentration is exactly why the pull keeps climbing instead of fading. Here is a number that captures how extreme this pull becomes. The force inside a stretched flux tube has been measured at roughly 16 tons of tension, packed into a string thinner than the width of a proton. 16 tons sits close to the weight of 3 adult elephants. All of that force concentrated into a thread far too small for any microscope to see directly, pulling on a single particle lighter than almost anything else in the known universe. Keep pulling, and the tension in that flux tube keeps rising without limit. This detail separates the strong force from every other force in physics. Stretch a spring far enough, and eventually it snaps, releasing tension instantly. A flux tube behaves differently. Something else happens first, something that has never once failed to happen in any experiment ever run. The energy stored inside that stretching flux tube keeps building, climbing higher every fraction of an inch the quark travels, until the tube holds an amount of energy dense enough to create brand new matter out of nothing. That threshold gets crossed remarkably fast, usually within a distance smaller than the width of a single proton, roughly 1/4,000,000th of a meter. Long before your imaginary tweezers could pull the quark any meaningful distance away, that stored energy reaches a breaking point far stranger than a simple snap. A 15-year-old holding one end of a rope tied to an elephant would feel a small taste of this. Pull gently, and the rope stays slack enough to move. Pull harder, and the rope tightens until your arms cannot add any more force, the tension maxing out long before the elephant ever budges. Quarks face a version of this pull that never maxes out, never releases, and never once allows the far end to break free. What happens at that breaking point is far stranger than a simple snap. It marks the exact moment the universe manufactures brand new matter out of raw energy, conjuring a replacement partner from nothing, an event so strange that physicists needed decades of careful experiments to confirm it was actually happening. That moment is where the story goes next. Every force you have felt in daily life weakens with distance. Push a friend on a swing, and your hand only matters while it touches them. Throw a ball, and gravity's pull weakens slightly the higher it climbs. Even the pull of a planet fades the farther a spacecraft travels away from it. This pattern feels so universal that most people assume every force in nature must work the same way. The strong force breaks that pattern completely, and confirming exactly how it breaks the pattern took physicists decades of careful measurement. Instead of fading with distance like every familiar force, the strong force holding quarks together grows in strength the farther a quark tries to travel. Double the distance between a quark and its partners, and the pulling force does not weaken. It intensifies. The reason traces back to that flux tube covered in the last chapter, the narrow string of gluon energy connecting separating quarks. An ordinary force, like gravity or electromagnetism, spreads outward through space in every direction, like ripples spreading across a pond, growing weaker as the ripple covers more area. A flux tube refuses to spread out. It stays locked into a narrow string-like shape no matter how far it stretches, concentrating all its energy into an increasingly thin, increasingly tense connection. Nothing about the total force gets diluted by spreading, so the tension simply keeps climbing. A comparison captures the strangeness well. Imagine a tug of war rope that somehow gets tighter and harder to pull every single time either team takes a step backward. Ordinary ropes stay the same tension no matter how far apart the teams stand, assuming the rope does not stretch. A quark's connection acts like a rope that tightens itself automatically, adding more resistance with every inch gained, an opponent that never tires and never loosens its grip. Physicists measured just how fast this tension climbs, and the results stunned researchers when it was first confirmed experimentally. The force between separating quarks grows by roughly 1 ton of tension for every trillionth of a meter of additional distance, a rate of increase with no equivalent anywhere else in physics. Compare that to gravity, which follows the opposite pattern entirely, weakening by the square of the distance between two objects. Double the distance in gravity, and the pull drops to 1/4 of its original strength. Double the distance between quarks, and the pull can climb past double its original strength, sometimes far past it. This single property explains why every attempt to isolate a quark has ended the exact same way. Energy poured into separating two quarks does not go toward freeing them. It goes directly into strengthening the very force resisting the separation, a feedback loop that punishes every attempt to break it. The harder scientists push, the harder the universe pushes back, and no amount of additional energy has ever managed to tip that balance in the quark's favour. Somewhere past a certain point, adding more energy stops helping the escape attempt entirely and starts fueling something else, something the flux tube has been quietly building toward the whole time. That threshold arrives faster than most people expect, arriving within a distance far smaller than the width of a single atom, and crossing it triggers one of the strangest events confirmed anywhere in physics. Picture the flux tube from the last 2 chapters stretched to its absolute limit, holding tension equal to several elephants packed into a string thinner than an atom. Every extra fraction of an inch adds more energy into that stretching connection. Eventually, the flux tube reaches a point most people would expect to end in a snap, the same way an overstretched rubber band finally breaks. Something else happens instead, and it ranks among the strangest confirmed events in all of physics. The energy stored inside that stretched flux tube reaches a threshold high enough to create brand new matter, directly out of pure energy. This connects back to one of the most famous equations ever written. Energy equals mass times the speed of light squared, first proposed by Albert Einstein. That equation works in both directions. Mass can convert into energy, the process powering the sun and every star in the sky. Energy can also convert into mass, and that is exactly what happens inside a snapping flux tube. At the breaking point, the flux tube does not release its stored energy into empty space. Instead, that energy transforms directly into a brand new quark and a brand new antiquark, appearing out of what looks like nothing at all. This process happens within an unimaginably short window of time, faster than 1/1,000,000th of a second, too fast for any equipment on Earth to watch directly, though the aftermath gets captured in extraordinary detail by particle detectors. Here is where the trick becomes clear. That newly created quark instantly bonds with the escaping quark, forming a brand new colourless particle. Meanwhile, the newly created antiquark bonds with whatever quarks remained behind, forming a second brand new colourless particle. Instead of one lone, isolated quark, two entirely separate particles now exist where there used to be one. The original goal of freeing a single quark has failed completely, replaced by an outcome that keeps every single quark trapped inside a colourless group, exactly as the universe demands. A comparison helps make sense of something this bizarre. Imagine cutting a piece of string in the middle, expecting two loose ends. Instead, the instant the cut happens, a fresh new knot ties itself onto each cut end automatically, so neither end is ever actually loose. Scientists have run this test more times than any other experiment in particle physics history, smashing protons and heavy atomic nuclei together at nearly the speed of light, and the flux tube has never once simply snapped and released a lone quark into open space. This single event, matter being born directly out of stretched stored energy, offers one of the clearest confirmed demonstrations that energy and matter are two versions of the same underlying thing. It also explains something that sounds almost too strange to be true. Empty space is never actually empty. Enough energy poured into a small enough space can conjure real, solid, measurable particles directly out of nothing, a process physicists have captured and measured thousands of times. What comes out of that snap rarely stops at just two new particles. Far more often, an entire cascade begins, one snap triggering another, then another, until dozens of particles come spraying outward together. That spray has a name, and it is the closest thing physicists have to a fingerprint left behind by an escaping quark. Something happened inside that snapping flux tube from the last chapter that deserves a closer look, because it may be the strangest confirmed fact in this entire story. Real, solid particles, particles with actual mass, appeared directly out of energy, out of what looked like completely empty space. This has already been measured directly, over and over again, inside particle accelerators around the world, confirmed as fact rather than left as an untested theory. Pack enough energy into a small enough region, and that energy converts into brand new matter, following the exact exchange rate Albert Einstein calculated over a century ago. Mass and energy are two forms of the same underlying currency, constantly convertible from one into the other, and a stretched flux tube snapping apart is one of the cleanest examples of that conversion physicists have ever captured. Here is a comparison that makes the scale easier to picture. Imagine an empty, sealed room, containing no matter at all, not even a single dust particle. Pump enough pure heat energy into that room without adding any physical material whatsoever, and solid objects begin appearing inside it out of nowhere, built directly from that heat. That sounds like magic in an empty room, yet it comes close to a literal description of what happens inside a proton collision billions of times every second at particle accelerators around the world. The amount of energy required to create a single pair of quarks stays remarkably small on an everyday scale, yet the process happens constantly, an estimated trillions of times every second inside every proton and neutron that exists, everywhere in the universe, including every atom inside your body right now. Quark-antiquark pairs wink into existence and disappear again constantly, a background hum of matter creation happening far too fast and far too small for anyone to notice. Physicists have a name for particles that flicker into existence and vanish again almost instantly: virtual particles. These particles exist for such a short window of time that measuring them directly is nearly impossible, yet their effects show up clearly in precise experiments, confirmed again and again across decades of research. Some virtual particles, especially the ones created inside a snapping flux tube, stick around long enough to become fully real, detectable, measurable particles captured by detectors and studied in detail. Here is the detail that connects everything back to something personal. This same process of energy converting into matter happens inside every proton in your body at this exact moment, contributing directly to your own mass. Nearly all of your weight traces back to a constant chaotic storm of energy, converting into particles, colliding, and converting back into energy again, over and over, trillions of times every second, inside every proton and neutron that makes up your entire body, far more than to any solid little balls of matter sitting still and unchanging. Stop and consider what that means. The number on a bathroom scale, the number most people spend their whole lives worrying about, mostly reflects the energy of a hidden storm happening inside atoms, rather than the mass of solid particles sitting quietly in place. That detail becomes the central mystery of this entire story, and it starts making full sense only after seeing what happens when all these newly created particles come spraying outward together, caught red-handed by detectors built specifically to catch them. Every time scientists try to rip a quark free from a proton, and every single attempt fails, the failure leaves behind evidence. That evidence has a name: a jet, a tight cone-shaped spray of particles racing outward from the collision point, all moving roughly in the same direction the original escaping quark was travelling. Jets form because of the chain reaction covered in the last 2 chapters. A quark tries to escape, the flux tube connecting it stretches and snaps, new quarks and antiquarks appear out of pure energy, and those new particles instantly combine into fresh, colourless particles. Those fresh particles are usually unstable, decaying within fractions of a second into smaller, more stable particles, which sometimes decay again into even smaller particles. By the time this cascade finishes, dozens of particles stream outward together in a tight, narrow spray, all clustered along the path the original quark was trying to take. Detectors built at facilities like the Large Hadron Collider are designed specifically to catch and measure these sprays. Picture a detector the size of a 7-story building, packed with layers of sensors precise enough to track the path of a single particle, smaller than an atom. When 2 protons collide, cameras and sensors capture the resulting jets, in extraordinary detail, timing and tracking every particle well enough for physicists to reconstruct which direction the original quark was heading, before it vanished into the spray. A useful comparison helps picture this. Imagine throwing a water balloon at a solid brick wall. The balloon itself never survives the impact intact. Instead, water sprays outward in every direction, but studying the pattern of that spray carefully enough reveals exactly where the balloon hit, and roughly how fast it was travelling. Jets work the same way. Physicists never see the original quark directly, the same way nobody sees the original water balloon after it bursts, but the spray of resulting particles reveals almost everything about the vanished quark that caused it. Here is a number that shows just how often this happens. At the Large Hadron Collider, proton collisions occur roughly 1 billion times every second, and jets show up in a significant share of those collisions, making them one of the most common and most carefully studied signatures in all of particle physics. Scientists have used decades of jet data to confirm nearly every prediction made about how quarks and gluons behave, turning something invisible into one of the most measurable phenomena in the entire field. Jets also carry a strange kind of memory. The number of jets produced in a single collision, along with their direction and energy, reveals how many quarks and gluons were involved in the original collision, and roughly how they were arranged. 2 jets flying outward in opposite directions usually signal a simple quark and antiquark pair being created and immediately trying and failing to separate. 3 or more jets can signal a gluon jumping into the mix, adding its own spray to the pattern. Every jet ever recorded tells the same underlying story. A quark tried to leave, and the universe refused to let it travel alone. That refusal has been captured, measured, and confirmed so many times that physicists consider it one of the most solid, well-tested facts in their entire field. Getting close enough to actually see that refusal happen required building some of the most extreme machines humanity has ever constructed. Machines capable of recreating conditions closer to the birth of the universe than anything else on Earth. Underneath the border of France and Switzerland sits a tunnel 17 miles around, cooled colder than outer space, built to do one specific job: smash protons together hard enough to catch a glimpse of the particles hiding inside them. This machine is called the Large Hadron Collider, and it stands as the largest and most powerful machine ever built by humanity. Protons inside this tunnel travel in two beams, moving in opposite directions, accelerated to a speed just a tiny fraction below the speed of light itself. At that speed, a single proton could circle the entire 17-mile tunnel more than 11,000 times every second. Magnets stronger than anything found in a typical hospital, cooled down to nearly absolute zero, the coldest temperature physically possible, bend these beams into a perfect circular path, keeping billions of protons locked in formation as they race toward a collision point. When two beams finally cross paths, protons smash into each other with tremendous force, releasing energy concentrated into a space smaller than an atom. That single collision briefly recreates conditions closer to the first tiny fraction of a second after the universe began than anything else humans have ever produced. For an instant far too short to measure directly, temperatures inside that collision point spike past 10 trillion degrees, hotter than the core of any star in the sky. Here is the detail that makes this entire enormous project necessary in the first place. Quarks and gluons stay too small and too tightly confined for any camera or microscope to ever observe directly, no matter how advanced the technology becomes. The only way to study them is indirectly, by smashing particles together hard enough to briefly stress the confinement rule, then carefully analysing the spray of jets and particles that comes flying outward afterward. Every insight in this story so far, the flux tube, the colour rule, the constant creation of matter from energy, was confirmed this exact way, through indirect evidence gathered from millions upon millions of collisions. The scale of data involved is difficult to picture. The Large Hadron Collider produces roughly 1 billion collisions every single second when running at full power. Sensors and detectors capture measurements from a tiny fraction of those collisions, the ones considered interesting enough to analyse, yet even that fraction adds up to more data every year than every streaming video service on Earth combined. Supercomputers filter through that flood of data looking for patterns matching predictions made decades earlier by physicists working entirely with pencil, paper and mathematics, long before any machine existed capable of testing their ideas directly. A comparison helps capture just how difficult this search really is. Imagine trying to figure out the exact shape of a snowflake by throwing it at a brick wall at nearly the speed of light and studying the splash pattern left behind, then repeating that same test billions of times every second. That comparison barely captures the actual difficulty involved, yet physicists have pulled it off successfully, confirming prediction after prediction with stunning precision. Building a machine this extreme took an international collaboration spanning more than 100 countries and tens of thousands of scientists and engineers, all working toward one core purpose: catching a shadow, an indirect trace, of particles the universe refuses to ever let anyone see directly. The very first hints that this shadow was real came from a far simpler experiment, decades earlier, one that first proved quarks were more than just an equation on a chalkboard. Long before the Large Hadron Collider existed back in the late 1960s, physicists faced a serious problem. A theory proposed that protons and neutrons were built from smaller particles called quarks, but the theory existed entirely on paper, built from mathematical patterns that fit the data without offering direct proof. Many physicists at the time doubted quarks were physically real at all, suspecting them to be nothing more than a useful mathematical trick. An experiment at the Stanford Linear Accelerator Center in California changed that completely. Researchers built a machine roughly 2 miles long, designed to fire electrons at a target made of hydrogen, essentially firing electrons directly at single protons. The goal was simple to describe, difficult to execute. Scientists wanted to see exactly how those electrons bounced off the protons, hoping the pattern of that bounce would reveal what protons were actually built from. Here is why this experiment mattered so much. A smooth, solid ball with no internal structure would send electrons bouncing off gently, deflecting only slightly, similar to a ball bouncing off a smooth wall. A proton containing smaller, hard, densely packed particles inside it would instead cause some electrons to strike one of those particles directly, bouncing backward at extreme angles, a result that would only make sense if something small, hard, and concentrated existed hiding inside the proton. The second outcome is exactly what researchers found. A surprising number of electrons bounced backward at sharp, unexpected angles nobody could explain if a proton was smooth and uniform throughout. Scientists compared this discovery to a famous earlier experiment from decades before, where physicist Ernest Rutherford fired particles at a thin sheet of gold, discovering that atoms contained a dense, tiny nucleus buried inside mostly empty space. The proton experiment revealed something remarkably similar. Protons turned out to be mostly empty space, containing small, hard, point-like objects buried inside, rather than smooth, solid spheres. This result offered the first direct experimental evidence that quarks were physically real, extending far beyond a convenient mathematical pattern invented to organize data. The discovery earned 3 of the researchers involved the Nobel Prize in Physics decades later, in 1990, recognizing an experiment that fundamentally changed how physicists understood the building blocks of ordinary matter. A comparison helps capture what this discovery actually revealed. Imagine throwing tennis balls at a closed cardboard box, unsure what is hiding inside. Most balls thrown at the box would bounce off the surface gently. If the box secretly contained a handful of steel marbles scattered inside, every so often a tennis ball would strike one of those marbles directly, ricocheting backward at a sharp, unexpected angle. Track enough of those sharp ricochets, and you could figure out that hard, small objects exist hidden inside the box without ever actually opening it or seeing them directly. That is essentially what physicists accomplished with protons, confirming that something small and solid existed hiding inside them, based entirely on how electrons bounced away. This experiment also confirmed something else important. The particles hiding inside the proton carried fractional electric charges smaller than any particle physicists had ever confirmed before, exactly matching a strange prediction quark theory had made years earlier. That detail sealed the case. Quarks were real, confirmed through direct evidence rather than mathematics alone, and that confirmation opened the door to an even stranger discovery waiting just beneath the surface, a discovery about exactly how quarks behave the closer you get to them. Everything covered so far points toward one clear pattern. Pull a quark away from its partners, and the force resisting the pull grows stronger and stronger, eventually forcing new matter into existence rather than allowing a lone quark to escape. A natural question follows from that pattern. What happens to that same force at extremely close range, when quarks sit almost directly on top of each other? The answer surprised physicists so completely that discovering it earned a Nobel Prize in Physics in 2004. At extremely short distances, closer together than quarks typically sit inside an ordinary proton, the strong force nearly vanishes. Quarks packed tightly together barely feel any pull toward each other at all, moving almost as freely as particles with no force acting on them whatsoever. Physicists named this strange behavior asymptotic freedom, and it flips the entire pattern of the strong force completely upside down compared to distance. This discovery makes far more sense with a comparison. Picture the flux tube from earlier chapters as a coiled spring lying loose on a table. Push the two ends close together and the spring goes slack, offering almost no resistance at all, allowing the ends to wiggle around freely. Pull the two ends apart and the spring begins resisting immediately, tightening more and more the farther the ends travel. Quarks behave in exactly this pattern. Squeeze them close together and the connection between them goes nearly slack. Pull them apart and the connection tightens into the powerful, unbreakable pull covered in the earlier chapters. Here is why this discovery mattered so much to physicists working to understand quarks. Asymptotic freedom explained why the electron scattering experiment from the last chapter succeeded in the first place. Electrons fired at protons were striking quarks that, for a brief instant during the high-energy collision, were behaving almost like free independent particles, barely influenced by the strong force at all. That freedom is exactly what allowed those electrons to bounce backward at sharp angles, revealing the hard, point-like particles hiding inside. A constant strong force at every distance, would have erased that clean scattering result entirely. Asymptotic freedom also solved a mathematical puzzle that had stumped physicists for years. Most forces in physics get easier to calculate at short range and harder to calculate at long range, because the math involved tends to spiral out of control the stronger a force becomes. The strong force flips this completely. Calculations involving quarks packed closely together, where the force nearly vanishes, stay relatively manageable. Calculations involving quarks stretched far apart, where the force grows toward infinity, become nearly impossible using ordinary mathematical methods, a problem that eventually pushed physicists toward an entirely different approach involving supercomputers, a strategy covered later in this story. A number worth sitting with. Physicists measured that at distances roughly 100 times smaller than the width of a proton, the strong force drops to a small fraction of its normal strength, weak enough that quarks packed at that range behave almost like they are not connected at all. Zoom back out to the normal size of a proton, and that same force climbs back to its full, overpowering strength within an incredibly short distance. This strange flip, weak up close, overwhelming far away, ties directly back to a detail mentioned earlier in this story. Gluons carry color charge themselves, unlike the particles carrying every other force in physics, and that single difference turns out to be the deep mathematical reason behind both extremes of this behavior. Every other force carrier particle in physics follows a consistent rule. Photons carry the electromagnetic force without being electrically charged themselves. The particles carrying the weak nuclear force, responsible for certain kinds of radioactive decay, do carry a small amount of charge, but nowhere near enough to interact strongly with themselves. Gluons break this pattern completely, and that single break explains nearly every strange property covered so far in this story. Gluons carry color charge, the exact same property carried by quarks. This means gluons do more than simply carry the strong force between quarks the way a mail carrier delivers letters without opening them. Gluons interact directly with each other, attracting, repelling, and even transforming into pairs of other gluons, adding layer after layer of complexity that no other force in physics has to deal with. A comparison makes this easier to picture. Imagine ordinary mail carriers who deliver letters between houses but never interact with each other directly, simply passing messages back and forth between separate addresses. Gluons behave like mail carriers who constantly bump into each other on the street, exchange their own letters between themselves, sometimes splitting into two separate carriers mid-delivery, tangling the entire delivery system into a chaotic web that grows more complicated the farther any single letter needs to travel. This self-interaction is the deep reason behind both asymptotic freedom and the ever-tightening pull covered in earlier chapters. At extremely short distances, gluon self-interactions partially cancel each other out, weakening the overall force and explaining why quarks packed closely together feel barely any pull at all. At longer distances, those same self-interactions start reinforcing each other instead, concentrating the force into the narrow, ever-tightening flux tube described earlier. No other force in physics behaves this way, because no other force carrier interacts with itself in this manner. Physicists confirmed gluon self-interaction directly through a specific kind of collision called a three-jet event. Earlier chapters explained that colliding a quark and an antiquark typically produces two jets flying outward in opposite directions. Occasionally, a third jet appears alongside the usual two, and that extra jet comes from a gluon being radiated directly out of the collision, behaving as its own separate, independently travelling particle. The first clear confirmation of three-jet events came from an experiment in Germany in 1979, offering direct proof that gluons could travel and behave as real particles capable of interacting on their own, rather than simply as passive carriers of force between quarks. Here is a detail that captures how deeply this single property, gluon self-interaction, reshapes the entire theory. Physicists needed an entirely new branch of mathematics just to handle equations where the force carrier interacts with itself this heavily. That branch of physics eventually became known as quantum chromodynamics, often shortened using its initials, the formal theory describing exactly how quarks and gluons interact through color charge. Every prediction covered throughout this story, confinement, asymptotic freedom, the ever-tightening flux tube, traces back to this single theory and the strange self-tangling behaviour of gluons driving nearly everything inside it. A question worth holding on to: the particle carrying the strongest force in the universe interacts constantly with itself, tangling and reinforcing its own pull the farther it stretches. Comparing that behaviour against every other force humanity has ever measured reveals something that makes gravity, the force most people consider the most powerful thing in the universe, look almost gentle by comparison. 4 fundamental forces govern the entire universe, as far as physicists have confirmed. Gravity holds planets in orbit and pulls every object toward the ground. Electromagnetism powers every light bulb, every phone screen, and every spark of static electricity. The weak nuclear force drives certain kinds of radioactive decay inside atomic nuclei. The strong force, the subject of this entire story, binds quarks together inside protons and neutrons. 3 of these 4 forces share a common pattern. Gravity, electromagnetism, and the weak force all weaken the farther apart 2 objects move, following mathematical rules that have held steady since scientists first began measuring them centuries ago. The strong force stands entirely alone, growing stronger instead of weaker as quarks move apart, a behaviour confirmed through decades of precise measurement and completely unmatched by any other force in nature. A side-by-side comparison makes the difference clear. Move the Earth twice as far from the Sun, and gravity's pull on the Earth drops to 1/4 of its current strength, following a mathematical pattern called an inverse square law. Move 2 electrically charged particles twice as far apart, and the electromagnetic pull between them also drops to 1/4 of its original strength, following that exact same inverse square pattern. Move 2 quarks twice as far apart, and the strong force pulling them together does not drop at all. It climbs, sometimes doubling or more, depending on exactly how far the separation stretches. Here is a number that puts the sheer strength of this force into perspective. At the short distances found inside an ordinary proton, the strong force measures roughly 100 times stronger than the electromagnetic force, and vastly stronger than gravity, which ranks as by far the weakest of the 4 fundamental forces despite feeling powerful in everyday life. Gravity only feels significant to humans because planets and stars contain such enormous amounts of mass concentrated in one place. At the scale of individual particles, gravity measures so weak that physicists usually ignore it completely when calculating how quarks and protons behave. A comparison helps put this strength difference into a picture anyone can hold on to. If gravity between 2 protons were represented by the weight of a single grain of sand, the strong force holding quarks together inside that same proton would be represented by something closer to the weight of an entire mountain range. That comparison reflects the actual measured ratio between how strongly these 2 forces pull on particles at extremely short range, rather than serving as an exaggeration. This extreme strength explains why the strong force only matters at extraordinarily short distances, despite ranking as the most powerful force known in the universe. Confinement locks that force entirely inside particles, like protons and neutrons, never allowing it to reach out and influence anything beyond an incredibly tiny range, roughly the width of an atomic nucleus and nothing farther. Gravity, by contrast, reaches across the entire universe, weak at every distance yet never fully disappearing, strong enough over billions of light years to hold entire galaxies together. Nature built the strongest force in the universe, then locked it inside a space smaller than anything the human eye could ever hope to see, hidden completely from the everyday world despite holding together every single atom that world is built from. Understanding exactly how strange and extreme that hidden force really is requires comparing it directly against gravity and electromagnetism side by side, laying all 3 forces out together to reveal a picture stranger than anything covered in this story so far. Picture 3 forces standing side by side, ready for direct comparison. Gravity, the force pulling you toward the ground and holding entire planets in orbit. Electromagnetism, the force powering every light, every phone, and every spark of static electricity. And the strong force, the force locked inside every proton and neutron in the universe, the central subject of this entire story. Start with gravity, the the force humans experience constantly and consider extremely powerful, yet gravity actually ranks as the weakest of the three by an enormous margin. Noticing gravity's pull at all requires an object as massive as an entire planet. A single proton exerts a gravitational pull on another proton so faint that detecting it directly has never been achieved by any instrument ever built. Gravity only becomes noticeable when enormous amounts of mass pile up together, which is exactly why planets and stars feel its pull so strongly, despite gravity being astonishingly weak at the level of individual particles. Electromagnetism ranks dramatically stronger than gravity at the particle scale, powerful enough to hold electrons in orbit around atomic nuclei, strong enough to spark lightning across entire storm clouds. Electromagnetism follows the familiar pattern most people expect from a force, weakening steadily the farther apart two charged particles move, the same inverse square pattern covered in the previous chapter. This force powers chemistry and shapes nearly every physical interaction humans experience directly in daily life, from touch to light to electricity itself. The strong force towers over both of these, roughly 100 times stronger than electromagnetism at the short distances found inside a proton, and functionally infinite compared to gravity at that same scale. Unlike the other two forces, the strong force refuses to follow the weakening pattern at all, instead growing more powerful the farther two quarks try to separate, a behaviour with no equivalent anywhere else in physics. This single difference locks the strong force into an incredibly short range, confined entirely inside particles like protons and neutrons, never once observed reaching beyond the width of an atomic nucleus. A single comparison brings all three forces together clearly. Picture gravity as a whisper, barely audible unless an entire stadium whispers together at once. Picture electromagnetism as a normal speaking voice, clear across an ordinary room, weakening the farther you walk from the speaker. Picture the strong force as a shout that gets louder the farther you walk away from it, a shout so powerful that nature had to sock it inside a room smaller than the human eye could ever see, the only way to keep it from overwhelming everything else in the universe. Physicists have confirmed all three of these forces through more than a century of combined experiments, matching predictions against measurements with extraordinary precision every single time. A fourth force still waits in this lineup, the weak nuclear force, responsible for the radioactive decay powering everything from smoke detectors to the sun itself, a force just as strange in its own right. What remains clear after placing all three forces side by side is this: the strong force stands alone, unmatched in raw power, unmatched in strangeness, locked inside a hiding place so small that humanity needed the largest, most expensive machines ever constructed just to catch a glimpse of it working. That hidden power sits inside every atom of your body right now, and the next stretch of this story pushes even deeper into exactly how tightly that power gets confined, starting with a single, narrow string of pure force stretched between two trapped and inseparable quarks. Every rule covered so far in this story has been confirmed through experiment, measured again and again inside particle accelerators around the world. A strange gap sits underneath all of that confirmed data. Nobody has ever proven, with pure mathematics alone, that confinement must happen. Physicists can calculate it. Physicists can predict it. Nobody has produced an airtight mathematical proof explaining why quarks are forced to stay locked together every single time, with zero exceptions. This gap carries a formal name inside mathematics, the Yang-Mills mass gap problem, named after two physicists who developed part of the underlying theory decades ago. The problem asks a deceptively simple question. The equations describing the strong force predict that force-carrying particles like gluons should behave as if they carry mass, even though gluons are measured as massless in every experiment ever run. Proving why that gap exists, cleanly and rigorously, using nothing but mathematics, has stumped some of the sharpest minds in the field for more than half a century. Here is why this problem matters so much. An institute in the United States called the Clay Mathematics Institute selected 7 of the hardest unsolved problems in all of mathematics back in the year 2000, naming them the Millennium Prize problems. Anyone who solves one of these 7 problems, with a complete and verified proof, receives $1 million. As of today, only one of the 7 problems has ever been solved, The Yang-Mills mass gap problem remains open, sitting unsolved on that list for over 2 decades, waiting for someone brilliant enough to close it. A comparison helps capture how strange this gap really is. Imagine an engineer who can build a bridge that stands perfectly for a century, tested under every possible weight and storm, yet cannot mathematically prove using pure physics why the bridge does not collapse. The bridge works. The evidence overwhelmingly confirms it works. A rigorous mathematical explanation for why it must always work remains just out of reach. Confinement occupies that exact same strange position inside physics. Thousands of physicists and mathematicians have attempted this problem since it was first named. Some have made partial progress, developing techniques that get closer to a full proof without quite closing the gap completely. Every attempt has revealed how deeply tangled the mathematics of the strong force truly is, filled with the same gluon self-interactions covered earlier in this story. Interactions so complicated that ordinary equations break down entirely at the distances where confinement takes hold. Universities and research institutes around the world still host regular workshops dedicated entirely to chipping away at small pieces of this problem, hoping incremental progress might eventually add up to a complete solution. Faced with a problem too difficult to solve using pen and paper alone, physicists eventually turned to an entirely different strategy. Instead of trying to prove confinement using pure mathematics, scientists built a way to simulate it directly, using some of the most powerful computers ever constructed. That strategy would eventually let physicists watch quarks behave inside a proton, one tiny calculated step at a time, without ever needing to solve the deeper mathematical mystery first. Building that strategy required rethinking how physics itself gets calculated, trading elegant equations for raw, brute force computation on a scale nobody had previously attempted. That strategy has a name, and it changed how physicists study the strong force forever. Solving confinement with pure mathematics has stumped physicists for decades. A different approach emerged instead, one that skips the impossible proof and simulates the answer directly. Physicists call this approach lattice quantum chromodynamics, usually shortened to lattice QCD, and it stands as one of the most computationally demanding calculations attempted anywhere in modern science. Here is the basic idea. Imagine slicing all of space and time into a grid, similar to graph paper stretched into 4 dimensions instead of 2. Each point on that grid represents a tiny possible location where a quark or gluon could exist. Physicists then run calculations at every single point on the grid, tracking how quarks and gluons might interact at each location, based on the known equations of the strong force. Repeat that calculation across billions of grid points, link every point together correctly, and a simulated picture of a proton begins to emerge, built entirely from raw computation rather than direct observation. The scale of computing power required for this task is difficult to picture. Some lattice QCD calculations have run on supercomputers capable of performing more calculations in a single second than every person on Earth could complete by hand across several lifetimes combined. Even with that staggering amount of computing power, a single detailed lattice QCD simulation of a proton can take months to finish, running continuously on machines that fill entire buildings and consume enough electricity to power a small town. Research institutions often share time on these supercomputers, scheduling months of calculation time years in advance, just to secure enough processing power for a single major simulation. A comparison helps make this method easier to picture. Imagine trying to predict exactly how a violin string vibrates, note by note, without ever touching the actual string. Instead, you break the string into millions of tiny segments on paper, calculate how each tiny segment would move based on the laws of physics, and then combine every one of those tiny calculations back together into a full prediction of the sound. Lattice QCD does something similar for an entire proton, breaking an impossible continuous problem into billions of small, solvable calculations that a computer can actually finish. This method has produced results that match real experiments with remarkable accuracy. Physicists have used lattice QCD to correctly calculate the mass of a proton, starting almost entirely from raw theory. matching the measured value to within a small fraction of a percent. That kind of agreement between pure computation and real-world measurement rarely happens in any branch of science, and it stands as one of the strongest confirmations that scientists truly understand the deep rules governing quarks and gluons, even without a full mathematical proof of confinement itself. Lattice QCD calculations have revealed something else worth remembering. Confinement holds steady across every single simulation ever run, with zero exceptions found inside the computer models either. Every simulated attempt to separate a quark inside these massive calculations ends the exact same way real experiments do, with new particles forming before a lone quark can ever escape. That consistency, appearing inside both real experiments and simulated mathematics, stands as some of the strongest evidence physicists have that confinement represents a fundamental law of the universe rather than a strange coincidence, a conclusion drawn from two completely independent methods that keep arriving at the exact same answer. Every rule covered throughout this story points toward one unbroken pattern. Quarks stay locked together, forever, without a single confirmed exception. A discovery from the last few decades reveals one place in the entire universe where that pattern briefly breaks down, and it happened at the very beginning of everything that exists during a window of time shorter than anything else described so far in this story. For a fleeting moment right after the universe began, temperatures reached levels so extreme that confinement itself could not hold quarks together. Instead of being locked inside protons and neutrons, quarks and gluons roamed freely through a scorching, chaotic soup of matter, unbound and unrestricted for the only confirmed stretch of time in the entire history of the universe. Physicists named this state quark-gluon plasma, and creating it inside a laboratory ranks among the most extreme achievements in the history of science, requiring machines specifically engineered to briefly recreate conditions unmatched anywhere else since the dawn of everything. Here is why heat matters so much to confinement. Earlier chapters explained how the strong force pulling quarks together grows stronger with distance, powered by that narrow flux tube of gluon energy. At extreme enough temperatures, packed densely enough together, quarks and gluons overlap so completely that individual flux tubes can no longer form cleanly between them. Without a clear flux tube connecting any two specific quarks, the usual rule of confinement temporarily loses its grip, and quarks briefly move freely through the surrounding plasma, instead of staying bound to specific partners, a genuinely temporary exception to a rule otherwise confirmed without fail everywhere else in the universe. The temperature required to melt confinement this way is almost impossible to picture. Scientists estimate quark-gluon plasma requires temperatures above roughly 1 trillion degrees, a number so extreme that it dwarfs the core of the Sun by a factor of tens of thousands. At that temperature, ordinary matter as anyone understands it simply cannot exist. Protons and neutrons cannot hold together, atoms cannot form, only a free boiling soup of quarks and gluons survives, exactly the state scientists believe filled the entire universe for a few millionths of a second right after everything began. A comparison helps put this into perspective. Picture ice melting into water, then water boiling into steam, each stage requiring more heat to break stronger bonds between molecules. Quark-gluon plasma represents an entirely new stage beyond even the hottest steam imaginable, a stage where the breaking bonds sit between quarks themselves, the smallest confirmed pieces of matter in existence, rather than between molecules or atoms. Reaching that stage requires temperatures so far beyond anything found naturally on Earth that scientists had to build machines specifically designed to recreate it. This discovery reshapes how confinement should be understood. Confinement is not some unbreakable law woven permanently into the fabric of reality under every possible condition. It represents the normal state of matter at every temperature the universe has experienced since those first fleeting moments after creation, broken only once, briefly, under conditions extreme enough to melt the very rule holding quarks in place. Recreating that broken moment, right here on Earth, required building machines capable of smashing entire atomic nuclei together with more violence than anything else humans have ever attempted. A project that took decades of planning and engineering before the first successful collision. Recreating the conditions of the early universe sounds like something confined entirely to theory, an idea physicists calculate on paper but never actually witness directly. Scientists have done exactly that, inside real machines, using real atomic nuclei smashed together with enough force to briefly melt confinement itself, an achievement that took decades of engineering and planning before the first successful attempt. Two major facilities on Earth specialize in this exact task: the relativistic heavy ion collider, located at Brookhaven National Laboratory in New York, and the Large Hadron Collider, located near Geneva, Switzerland. Both run special experiments where they abandon ordinary protons and instead accelerate entire heavy atomic nuclei, most often gold or lead, smashing them together at speeds approaching the speed of light, a strategy entirely different from the ordinary proton collisions covered in earlier chapters. Here is why heavy nuclei work so much better than single protons for this task. A single proton contains only 3 quarks, far too few to generate the sustained temperature and density needed to melt confinement across any meaningful region of space. A gold nucleus contains nearly 200 protons and neutrons bound together, packed with hundreds of quarks in total. Smashing 2 gold nuclei together concentrates an enormous number of quarks and gluons into an incredibly small space all at once, generating both the temperature and the density required to briefly recreate quark-gluon plasma, a feat impossible to achieve using single, isolated protons alone. The moment of collision unleashes conditions that sound almost impossible to summarize accurately. For an instant lasting only a few trillionths of a trillionth of a second, the collision point reaches a state closer to the first microseconds after the universe began than anything else ever produced by human technology. Matter briefly exists as a free-flowing plasma of quarks and gluons, expanding and cooling almost immediately, then rapidly recombining back into ordinary particles as confinement reasserts itself within an unimaginably short window of time. A comparison helps capture the strangeness of studying something this brief. Imagine trying to study the exact moment a snowflake forms by melting an entire glacier down to liquid water, then instantly refreezing a tiny droplet of that water fast enough to capture the very first crystal forming. Physicists face a similar challenge, studying a state of matter that exists for a period of time too short for direct observation, forced to reconstruct what happened by carefully analysing the particles that come flying outward once confinement locks back into place. Detectors surrounding these heavy ion collisions track thousands of particles streaming outward from each collision, measuring their energy, direction and type with extraordinary precision. By studying patterns across millions of these collisions, physicists have confirmed that quark-gluon plasma behaves less like an ordinary gas and more like a nearly frictionless liquid, flowing and rippling in ways nobody fully expected before the first successful experiments. Researchers have compared this discovery to expecting a violent explosion, and instead finding something closer to a smoothly swirling whirlpool, an outcome that reshaped how physicists model the earliest instance of the universe. That liquid-like behaviour offers scientists their closest possible glimpse into the actual physical state of the entire universe during its first fleeting instance of existence, a window into creation itself recreated for a fraction of a second inside a machine built by human hands. Numbers alone rarely capture how extreme these heavy ion collisions truly become. A single collision between 2 gold nuclei smashed together at nearly the speed of light briefly reaches a temperature exceeding 4 trillion degrees, a number confirmed through careful measurement at Brookhaven National Laboratory. That temperature dwarfs the core of the Sun, which burns at a comparatively modest 15 million degrees, meaning a single gold-on-gold collision briefly runs hotter than the Sun by a factor of roughly 250,000, a difference too large for most everyday comparisons to properly capture. Here is a comparison that helps put a number like that into perspective. Picture every star visible in the night sky, and picture the hottest one among them, a blazing blue giant far hotter than our own Sun. Even that blazing blue giant, one of the hottest naturally occurring objects known anywhere in the universe, still falls short of the temperature reached inside a heavy ion collision, lasting only a fraction of a second inside a laboratory on Earth, a fact that still surprises most people the first time they hear it. For that brief instant, the hottest point in the entire visible universe exists inside a particle detector built by scientists chasing an answer about the earliest moments of existence, rather than inside any star. Reaching that temperature requires accelerating gold nuclei to roughly 99.9% of the speed of light before collision. At that speed, each gold nucleus carries an almost unimaginable amount of kinetic energy packed into an object smaller than the width of a human hair. When two of these nuclei finally collide head-on, nearly all of that kinetic energy converts almost instantly into heat and newly created matter, following the same energy to mass conversion covered earlier in this story, except scaled up to a level involving hundreds of quarks all interacting together at once instead of just one escaping quark inside a single flux tube, producing a fireball far denser and far hotter than anything a single proton collision could ever generate. A detail worth sitting with makes this achievement even stranger. This extreme temperature exists for an almost impossibly short window of time, far less than a trillionth of a second, before the expanding fireball cools rapidly and confinement reasserts itself, locking quarks back into ordinary particles. Scientists have compared the entire lifespan of a single quark-gluon plasma event to trying to photograph a single lightning strike using a camera that can only capture one frame every few years. Catching that fleeting moment at all required building detectors precise enough to reconstruct an event that finishes before most other physics experiments would even finish starting up. This achievement carries weight beyond simply breaking a temperature record. Every successful heavy ion collision offers physicists a genuine physical glimpse into the state of the entire universe during its first few millionths of a second of existence, a period otherwise completely inaccessible to any telescope or observation method available anywhere on Earth. Confirming exactly how that primordial soup behaved, how it flowed, and how quickly it cooled back into ordinary matter has reshaped scientific understanding of how the universe transitioned from an unimaginably hot quark-filled plasma into the ordinary protons, neutrons, and atoms that eventually built every star, every planet, and every living thing that has ever existed. Every earlier chapter in this story hinted at a mystery worth returning to directly. The three quarks trapped inside a proton barely weigh anything on their own, adding up to less than 2% of the proton's total mass. The remaining 98% had to come from somewhere, and physicists eventually traced that missing mass back to a strange, precise mathematical effect hiding inside the very structure of the strong force, an effect that took decades of combined theoretical and experimental work to finally pin down with confidence. Physicists call this effect the trace anomaly, and understanding it requires revisiting a concept from earlier in this story. Ordinary theories in physics often contain a property called scale symmetry, meaning the underlying equations look the same no matter how large or small the system being studied happens to be. The basic equations describing quarks and gluons start out with this property built in, suggesting nothing about the theory should generate an inherent size or mass on its own, at least according to the raw mathematics alone. Something breaks that symmetry the instant those equations get applied to a real, physical proton. The strong force, growing wildly stronger at increasing distance, and confining quarks into a fixed, specific size, quietly destroys the scale symmetry the underlying equation started with. That broken symmetry is not a flaw or a mistake. It represents a real, measurable physical effect, confirmed through decades of both experiment and lattice QCD calculation, and it carries a very specific consequence. Breaking scale symmetry generates an inherent energy scale inside the proton, an energy tied directly to confinement itself, and that energy converts directly into the missing mass physicists had been searching for. A comparison helps make an idea this abstract easier to hold on to. Picture a perfectly smooth, symmetrical rubber sheet stretched flat in every direction, containing no particular size built into it at all. Now, imagine pinning that sheet down at several tightly spaced points, forcing it to bunch, fold, and hold a fixed size and shape it did not have before. The pins did not exist inside the original smooth sheet. The moment they get added, the sheet develops a specific, measurable structure that simply was not there beforehand. Confinement acts like that same set of pins, forcing quarks and gluons into a specific fixed structure, and that forced structure generates real, physical mass. Recent experiments have measured this effect directly, rather than relying purely on theory. Researchers at Jefferson Lab in Virginia used a technique involving particles called J divided by PSA mesons, produced by firing high-energy photons at protons to directly probe how the trace anomaly contributes to a proton's mass and internal pressure. Results published in the scientific journal Nature confirmed that this anomaly effect accounts for the overwhelming majority of a proton's total mass, closely matching decades of theoretical prediction. This single discovery answers one of the deepest open questions in all of physics. Nearly everything you weigh, nearly every atom holding your entire body together, traces its mass back to the confined, self-trapped energy of quarks and gluons locked eternally together by the strong force. Far more than to solid particles sitting quietly in place, a force so extreme it generates the very mass of ordinary matter simply by refusing to ever let go. Stop for a moment and consider what confinement actually means for you personally right now, sitting exactly where you are. Every single atom making up your body, every bone, every muscle, every strand of hair, depends entirely on a rule that traps quarks together with a force so extreme that nothing in the observable universe has ever managed to break it. A rule operating silently inside you at this exact instant, trillions of times over. Here is a fact worth sitting with directly. The number displayed on a bathroom scale, the number so many people spend enormous energy worrying about, mostly reflects confined energy trapped inside your protons and neutrons, not the mass of solid little particles sitting quietly inside you. Nearly all of your weight comes from the strong force itself, from the constant churn of gluons and virtual particles locked inside every proton and neutron throughout your entire body, an effect confirmed through the trace anomaly covered in the last chapter, measured directly through careful experiments rather than assumed from theory alone. A comparison helps make this personal connection land more clearly. Picture your entire body as a city built almost entirely from empty lots, with only a tiny handful of actual buildings scattered here and there. Nearly all the actual structure and substance of that city comes from an invisible, constantly working power grid running underneath everything, generating enough concentrated energy to give the entire city its true weight and presence, far more than from those scattered buildings themselves. Your body works in a strikingly similar way, mostly assembled from confined energy rather than from simple solid building blocks sitting passively in place. This connection reaches even deeper once you consider where the quarks inside your body originally came from. Every up quark and down quark inside every atom in your body formed during the earliest moments of the universe, inside that same scorching quark gluon plasma covered a few chapters ago, long before the sun, the earth, or any living thing existed anywhere. As the universe expanded and cooled, confinement locked those free-floating quarks into protons and neutrons for the first time. Protons and neutrons that eventually combined into the first atoms, then stars, then heavier elements forged inside dying stars, eventually scattering across space and reassembling into the atoms that build every person who has ever lived. Confinement created the ordinary matter making up stars and planets, and it shaped the very possibility of chemistry itself, extending far beyond simple matter creation alone. Without quarks locked permanently into stable protons and neutrons, atoms could never form in the first place, and without stable atoms, none of the complex chemistry required for stars, planets, or living organisms could ever have developed. Every single reaction happening inside your cells right now depends on atoms that only exist because confinement locked their internal quarks together billions of years ago and has never once let go since. A rule discovered through smashing subatomic particles inside massive underground tunnels turns out to be the same rule responsible for your own existence, holding together every atom that makes up your body, your breath, and your thoughts at this exact moment. Understanding just how fragile and extraordinary that arrangement really is requires asking a far stranger question, one physicists rarely discuss outside their own research meetings. What would actually happen if this rule ever failed? Physicists spend most of their careers confirming that confinement holds steady under every condition ever tested. A smaller, quieter conversation happens alongside that research, one physicists rarely bring up outside their own labs. What would actually happen if confinement ever failed under conditions nobody has yet managed to test? A question that sounds almost like science fiction until you realise serious researchers actually study it using real mathematics. This question is not idle speculation disconnected from real science. Physicists explore it seriously using the same mathematical tools covered earlier in this story, running calculations and simulations to understand exactly how fragile or robust confinement really is under extreme, currently untestable conditions. So far, every calculation, every simulation, and every experiment has confirmed confinement holds firm, but understanding the edges of that confirmation matters just as much as confirming the rule itself, since the edges of any rule often reveal the most about how it actually works underneath. One serious avenue of exploration involves extreme density rather than extreme temperature. Quark-gluon plasma, covered earlier in this story, breaks confinement through overwhelming heat. A separate, still largely theoretical possibility involves breaking confinement through overwhelming pressure. Instead, squeezing matter so densely that quarks might behave freely without needing extreme temperature at all. Nowhere on Earth can generate pressure anywhere close to what this would require, but one place in the known universe might come remarkably close. An object covered in detail in the next 2 chapters, spinning quietly somewhere among the stars overhead, invisible to the naked eye yet studied constantly through powerful telescopes. Another serious question physicists ask involves the deep, unproven mathematical connection between confinement and the mass of ordinary matter. If confinement somehow weakened under conditions not yet discovered, the trace anomaly covered a few chapters back suggests proton mass itself would shift as a direct consequence. Since nearly all visible matter in the universe depends on that confined mass, even a slight theoretical weakening in confinement would ripple outward into fundamental questions about how stable atoms, stars, and eventually life itself could ever have formed in the first place. Questions that touch nearly every branch of physics at once. A comparison helps frame why physicists take a hypothetical question this seriously. Engineers who build bridges do not simply trust that a bridge holds steady under normal traffic. They calculate exactly how much extra weight, wind, or stress the bridge could handle before failing, even though the bridge may never actually experience conditions anywhere close to that extreme limit. Physicists study hypothetical confinement failure with a similar mindset, driven by a desire to fully understand the limits of a rule and exactly where and how that rule could theoretically break, rather than by any expectation that it will actually happen. Every test run so far, across every accelerator, every simulation, and every theoretical calculation, keeps returning the same answer. Confinement holds. It held during the extreme heat of quark-gluon plasma experiments. It held during every attempt to pull a quark apart using the most powerful machines ever constructed. The only place left where nature herself might be running an experiment physicists cannot replicate sits buried inside one of the strangest, densest objects known anywhere in the universe, spinning quietly in the darkness of deep space, far beyond the reach of any laboratory ever built on Earth. Somewhere in the darkness of deep space, dead stars collapse into objects so dense that a single teaspoon of their material would weigh more than every car ever manufactured on Earth combined. These objects are called neutron stars, and they represent one of the most extreme environments known anywhere in the universe, extreme enough that physicists genuinely wonder whether confinement itself might be tested at their very core, a possibility that connects the smallest particles in this story to some of the largest gravitational forces known to exist. Neutron stars form when a massive star runs out of fuel and collapses under its own gravity, crushing its remaining material into an object often no larger than a mid-sized city, despite containing more mass than an entire sun. That collapse generates gravitational forces strong enough to crush ordinary atoms completely, forcing electrons and protons to merge together into neutrons, packing matter into a density unmatched anywhere else in the observable universe outside a black hole itself, a density that pushes ordinary physics to its breaking point. Here is why physicists connect neutron stars directly back to confinement. Ordinary matter, including the protons and neutrons covered throughout this entire story, exists at relatively modest densities compared to what might exist deep inside a neutron star's core. As gravity crushes material tighter and tighter toward the center of a neutron star, densities eventually reach levels far beyond anything ever tested inside a particle accelerator on Earth. At some theoretical density, a density physicists have not yet confirmed exists anywhere in the real universe. Neutrons themselves might get squeezed so tightly together that their individual boundaries start to overlap, potentially allowing the quarks trapped inside them to interact directly across what used to be separate particles. A comparison helps capture just how extreme this squeezing really becomes. Imagine packing an entire ocean's worth of water into a single drop, then continuing to compress that same drop down even further, past any density water could survive as a liquid at all. Neutron star material behaves in a similarly extreme way, compressed so far beyond ordinary matter that the very identity of individual particles becomes genuinely uncertain deep inside the core. Scientists have not directly confirmed what state matter takes at the exact centre of a neutron star, since no telescope or instrument can see that deep inside such a distant, extreme object. Indirect evidence comes from studying how neutron stars behave from the outside, measuring their mass, their size, and how quickly they spin, then comparing those measurements against theoretical models built using the same lattice QCD calculations covered earlier in this story. Some of those models suggest the innermost core of the most massive neutron stars might reach densities high enough to squeeze confinement to its absolute theoretical limit, potentially allowing quarks to briefly exist in a state closer to freedom than anything ever measured directly here on Earth. This possibility remains genuinely unconfirmed, sitting right at the edge of current scientific understanding. If true, it would mean the most extreme test of confinement anywhere in the universe is happening constantly, deep inside collapsed stars scattered across the galaxy, completely hidden from direct observation, monitored only through indirect signals like gravitational waves and precise measurements of starlight. And that possibility leads directly into an even stranger hypothetical object that might exist somewhere in the darkness beyond. Push the extreme density inside a neutron star even further, past the theoretical limit where quarks might begin interacting freely across what used to be separate neutrons, and physicists arrive at a genuinely hypothetical object that has never been directly confirmed to exist anywhere in the universe. Scientists call this hypothetical object a quark star, and it represents the single most extreme possible test of confinement that current physics can imagine. A quark star, if such an object truly exists, would form under conditions even more extreme than an ordinary neutron star, with gravity crushing matter so completely that individual neutrons stop existing as separate particles entirely. Instead, the entire core would exist as a continuous ultra-dense sea of quarks, no longer confined into individual protons or neutrons at all, held together instead by the sheer crushing gravity of the collapsed star rather than by the usual rules of confinement covered throughout this story, a genuine reversal of everything explored so far. Here is what makes this object so strange to consider seriously. Confinement, the unbreakable rule at the centre of everything covered so far, describes how quarks behave under ordinary conditions found throughout nearly the entire universe. A quark star would represent one of the only places where gravity might overpower confinement directly, replacing the strong force's usual grip with an even more overwhelming crushing force generated by the collapsed remains of a dead star. Quarks inside such an object would not be roaming freely the way they briefly did inside quark gluon plasma either. They would instead exist locked into an entirely different, ultra-dense state that physicists sometimes call quark matter, still poorly understood and still completely unconfirmed through direct observation. A comparison helps frame just how extreme and uncertain this remains. Imagine a mountain so tall and so heavy that its own weight eventually crushes solid rock into a completely different physical state, one that no geologist has ever directly observed or measured, existing only as a theoretical possibility calculated on paper. Quark stars occupy that exact same uncertain territory inside astrophysics, a theoretical endpoint calculated using the same equations that describe confinement, without a single confirmed observation, proving one actually exists anywhere in the sky. Some astronomers have proposed that a small number of unusually dense, unusually small neutron stars detected through telescopes might actually be quark stars in disguise, their measured size and mass sitting slightly outside what standard neutron star models would predict. None of these candidates have been confirmed. Every single one remains a plausible but unproven possibility, waiting for better telescopes, better gravitational wave detectors, or entirely new observation methods before scientists could ever confirm whether true quark matter exists anywhere in the real universe, a confirmation that would rank among the most significant astrophysical discoveries of the century. This hypothetical object represents the outer edge of everything explored so far in this story, a place where confinement, the rule proven unbreakable across every single laboratory experiment ever conducted here on Earth, might theoretically give way to something entirely different, driven by forces even more overwhelming than the strong force itself. Confirming or ruling out quark stars remains one of the most tantalizing open questions in modern astrophysics, and closing that question could reshape everything scientists currently understand about the outer limits of confinement. Confinement forces quarks into permanent partnerships, but the exact rules governing those partnerships hide more flexibility than most people realize. For decades, physicists assumed only two specific combinations of quarks could ever exist stably. 3 quarks bound together forming particles like protons and neutrons, or 1 quark paired with 1 antiquark forming lighter particles called mesons. Recent discoveries revealed that assumption was incomplete, opening up an entirely new catalogue of particles nobody had confirmed existed until relatively recently. Starting in the early 2000s and accelerating rapidly over the following 2 decades, physicists began confirming entirely new categories of particles built from 4 or 5 quarks bound together at once. Particles built from 4 quarks are called tetraquarks. Particles built from 5 quarks are called pentaquarks. Both categories fully obey the strict colourless rule covered earlier in this story, proving that confinement never actually broke to allow their existence. Nature simply found new, more complicated combinations capable of cancelling colour charge down to 0, hiding in plain sight until detector technology finally became precise enough to catch them. Here is why these particles surprised so many physicists when they were first confirmed. The colourless rule technically allows any combination of quarks and antiquarks that mathematically cancels to 0 colour charge overall, reaching well beyond the 2 simplest combinations physicists had focused on for decades. 4 quarks can combine their colours in specific patterns that cancel out completely, and so can 5, provided the mathematics lines up correctly. Confirming these exotic combinations actually existed in nature, rather than remaining purely theoretical possibilities, required extraordinarily precise detector technology capable of spotting incredibly rare, incredibly short-lived particles buried inside massive amounts of collision data. The Large Hadron Collider confirmed the first widely accepted pentaquark in 2015, detected through a specific extremely rare particle decay pattern that matched theoretical predictions almost perfectly. Since that discovery, physicists have confirmed several additional tetraquarks and pentaquarks, each one slightly different in mass and internal structure, expanding the known catalogue of particles built entirely from confined quarks, with new candidates still being investigated at detectors around the world. A comparison helps capture what makes these particles so unusual. Picture confinement as a strict rule requiring every dance to end with dancers arranged into a perfectly balanced formation. For decades, physicists only knew about 2 specific formations that satisfied the rule, a trio and a pair. Tetraquarks and pentaquarks revealed that 4 dancers, or 5 dancers, could also arrange themselves into balanced, rule-following formations, provided they positioned themselves correctly. The strict rule requiring perfect balance never actually changed. Physicists simply discovered new formations nobody had previously confirmed were possible. These exotic particles typically exist for an almost unimaginably short amount of time before decaying into more familiar particles, making them extraordinarily difficult to detect directly. Studying them offers physicists a valuable new tool for testing the strong force under configurations never previously observed, providing fresh data that helps refine lattice QCD calculations and deepen understanding of exactly how flexible or how strict the underlying rules of confinement truly are. Every newly confirmed tetraquark and pentaquark adds another confirmed data point, proving the same underlying truth that has held steady throughout this entire story. Confinement bends into unexpected new shapes, but it has never once broken, a pattern researchers expect to keep holding as detectors grow even more sensitive. Step back from exotic particles and extreme astrophysical objects for a moment, and consider something far more ordinary, sitting quietly all around you. Confinement reaches far beyond a strange rule confirmed inside massive particle accelerators. It represents the entire foundation supporting every atom, every molecule, and every chemical reaction that has ever occurred anywhere in the universe, from the simplest hydrogen atom to the most complex living cell. Here is why this connection runs so deep. Atoms require stable protons and neutrons sitting at their center in order to exist at all. Stable protons and neutrons require quarks locked permanently together, refusing to ever drift apart under normal conditions. Remove confinement, even briefly, and protons and neutrons could not hold their shape, atomic nuclei could not form, and the entire periodic table of elements, every substance ever studied in a chemistry classroom, would simply cease to exist, taking with it every star, every planet, and every living thing that depends on stable matter to survive. A comparison helps make this dependency easier to picture. Imagine an entire city built from countless interlocking bricks, each brick representing a single atom. Confinement plays the role of the mortar holding each individual brick together internally, keeping every single brick from crumbling apart before it ever gets placed into a wall. Without that internal mortar, no brick could ever hold its shape long enough to become part of any larger structure. The entire city, every building, every street, every foundation, depends completely on an internal rule, operating at a scale far too small for any single brick to notice directly. This dependency stretches far beyond simple chemistry class diagrams. Stars generate energy by fusing hydrogen atoms into helium, a process entirely dependent on stable protons capable of surviving the intense pressure and heat found inside a star's core. Without confinement holding those protons together, nuclear fusion could never occur, stars could never shine, and the heavier elements forged inside dying stars, the same elements that eventually became the calcium in your bones and the iron in your blood, could never have formed in the first place, leaving the universe permanently dark and empty of the complex chemistry needed for life. Confinement even shapes the basic properties defining how different elements behave chemically. The specific number of protons locked inside a nucleus determines which element an atom becomes, from hydrogen to oxygen to gold, and that specific number stays fixed only because confinement refuses to let quarks drift between different protons and neutrons under ordinary conditions. Every chemical bond, every reaction inside a living cell, every property that makes water behave differently from oxygen traces back, several layers deep, to this same unbreakable rule governing quarks first covered at the very beginning of this story. Confinement rarely gets mentioned in an ordinary chemistry classroom, buried underneath layers of more immediately visible rules about electrons, bonds, and reactions. Underneath every single one of those more familiar rules sits this same foundational law, quietly holding together the protons and neutrons that make chemistry possible in the first place. Understanding just how essential that foundation really is raises an obvious next question. One physicists are actively working to answer using the next generation of particle accelerators currently under construction, machines built specifically to probe deeper than anything that came before. Every discovery covered throughout this story came from indirect evidence, since no camera or microscope has ever directly observed a quark or gluon on its own. Scientists are currently constructing an entirely new machine specifically designed to study quarks and gluons with far greater precision than ever before. A facility called the Electron-Ion Collider, currently under construction at Brookhaven National Laboratory in New York, developed through a major collaboration with Jefferson Lab in Virginia, two of the leading nuclear physics facilities in the country. Here is what makes this new machine different from earlier colliders covered in this story. The Large Hadron Collider excels at smashing protons together with tremendous force, generating extreme conditions capable of briefly stressing confinement to its limits. That raw power comes with a trade-off, since violent collisions create messy, chaotic sprays of particles that can obscure finer details about how quarks and gluons actually arrange themselves inside an ordinary, undisturbed proton. The Electron-Ion Collider takes a gentler, more precise approach instead, firing electrons at protons and heavier atomic nuclei with carefully controlled energy, similar in spirit to the historic Stanford experiment covered earlier in this story, but with far greater precision and far more advanced detector technology. Physicists have nicknamed this new machine an electron microscope for the strong force, since its entire purpose involves mapping out exactly how quarks and gluons are distributed inside a proton, layer by layer, with a level of detail no previous experiment has achieved. Scientists particularly want to understand how gluons, the particles responsible for carrying nearly all of a proton's mass through the trace anomaly covered earlier in this story, are actually arranged and distributed throughout the interior of ordinary matter. A comparison helps capture the difference between this new approach and earlier experiments. Imagine trying to understand the inside of a sealed watermelon by throwing it against a wall as hard as possible, then studying the resulting mess of juice and seeds scattered everywhere. That approach reveals real information, but it destroys the delicate internal structure in the process. The electron-ion collider instead works more like carefully passing a beam of light directly through the watermelon, gently revealing its internal structure layer by layer without violently destroying the very thing being studied. Construction on the electron-ion collider began in the 2020s, with scientists expecting the machine to begin producing meaningful data sometime in the next decade. Once operational, researchers expect this machine to answer questions that have remained open throughout this entire story, mapping exactly how gluons generate proton mass through the trace anomaly, precisely measuring how quarks and gluons contribute to a proton's overall spin, and testing the limits of confinement with a level of precision never before achieved anywhere on Earth. This new machine represents the next chapter in a scientific pursuit stretching back more than half a century, from the earliest indirect evidence confirming quarks were real, through decades of increasingly powerful colliders smashing particles together with greater and greater force. The electron-ion collider shifts that pursuit toward precision instead of raw power, aiming to finally answer some of the deepest remaining questions about exactly how confinement builds the ordinary matter that makes up every star, every planet, and every person who has ever lived. Questions that have driven this entire investigation from its very first chapter. Every experiment covered throughout this entire story has confirmed the same unbroken outcome. No matter how much energy scientists pour into a collision, no matter how sophisticated their detectors become, quarks have never once been caught travelling alone through open space. A natural question follows from that unbroken record, one that pushes right against the edge of what current technology can test. Could some future machine, more powerful than anything built so far, ever finally succeed where every previous attempt has failed? Physicists generally consider this question from two very different angles. The first angle involves simply building bigger, more powerful colliders, continuing the same basic strategy that produced the Large Hadron Collider, hoping that enough additional energy might eventually overwhelm confinement directly. Several proposals for next-generation colliders currently exist on paper, including a proposed future circular collider that would dwarf the Large Hadron Collider in both size and power, potentially stretching across a tunnel more than 50 miles around, a project that would take decades and enormous international funding to complete. Here is why most physicists doubt this brute force approach will ever succeed, no matter how powerful future machines eventually become. Every chapter of this story has shown that confinement does not weaken. As more energy gets applied, it strengthens instead, and pouring in additional energy simply accelerates the creation of new quark pairs even faster than before, keeping every quark trapped inside a colourless particle, no matter how quickly the collision unfolds. Based on everything confirmed through decades of research, adding more raw power alone appears unlikely to ever break this pattern, since the underlying mathematics of the strong force predicts confinement should hold, regardless of how much energy gets thrown at it. The second angle physicists explore feels considerably stranger. Rather than trying to overpower confinement directly, some researchers study whether extreme conditions elsewhere in the universe, like the crushing density theorized inside neutron stars and quark stars covered earlier in this story, might reveal a genuine loophole physicists have not yet identified through laboratory experiments alone. Studying those extreme astrophysical environments, using telescopes and gravitational wave detectors alongside traditional particle accelerators, offers a completely different path toward testing the true limits of confinement, one that does not depend entirely on building ever larger machines here on Earth. A comparison helps frame where current science actually stands. Imagine spending decades testing a locked vault using every tool imaginable. confirming again and again that no amount of force manages to open it. At some point, continuing to build bigger tools to apply even more force stops being the most promising path forward. Instead, researchers start looking for a different kind of key entirely, studying the vault's construction more carefully rather than simply pushing harder against the same locked door, a shift in strategy that has already begun reshaping how physicists plan future experiments. For now, every serious scientific investigation continues to confirm the exact same outcome this entire story is traced from its very first chapter. Quarks stay locked together, permanently, without exception, regardless of how the question gets approached. Whether that outcome will ever change through a future collider, a breakthrough in astrophysics, or an entirely new idea nobody has considered yet, remains genuinely unknown, and that uncertainty leads directly into the single deepest, most unresolved question sitting underneath everything, covered throughout this entire story. Every discovery explored throughout this story answers a specific piece of a much larger puzzle. Quarks stay locked together because of an ever-tightening flux tube of gluon energy. That flux tube behaves the way it does because gluons carry color charge and interact constantly with themselves. Confinement generates nearly all of the mass inside ordinary matter through the trace anomaly. Every single one of these answers, confirmed through decades of careful experiment, still leaves one much deeper question sitting completely unresolved underneath all of them. A question that no accelerator or supercomputer has yet managed to answer. Why does nature enforce this rule in the first place? This question sits differently than everything explored so far in this story. Earlier chapters explained mechanisms, the specific processes and behaviors that make confinement happen the way it does. Nobody has yet explained why the universe operates according to these particular rules instead of some other possible set of rules entirely. Physicists can describe confinement with extraordinary mathematical precision. Explaining why the deepest laws of physics happen to work this way, rather than some other way entirely, remains a question science has not yet found a way to fully answer. A comparison helps frame just how deep this uncertainty actually runs. Imagine studying a game with rules so consistent that you can predict every single outcome with perfect accuracy, confirmed across millions of played rounds without a single exception. Understanding those rules perfectly still would not explain why the game was designed with those specific rules in the first place, rather than some other equally consistent set of rules that could have governed an entirely different universe instead. Physicists find themselves in a remarkably similar position with confinement, capable of predicting its behavior with stunning precision while still lacking any deeper explanation for why this particular rule exists at all. Some physicists explore this question through a broader idea called the anthropic principle, suggesting that a universe with different fundamental rules might never have produced stable atoms, stars, or eventually life capable of asking this exact question in the first place. Under that view, confinement exists the way it does, partly because any universe without a similar rule might never develop the complexity required to support curious, observing minds capable of studying the question at all. This idea remains deeply debated among physicists and philosophers alike, offering one possible perspective rather than a confirmed scientific answer, and it rarely satisfies researchers looking for a more direct mathematical explanation. Other physicists suspect a deeper, currently undiscovered theory might eventually explain why confinement takes the exact mathematical form it does, similar to how earlier breakthroughs in physics eventually explained rules that once seemed like unexplainable coincidences. Finding that deeper theory, if one truly exists, would likely require discoveries far beyond anything covered throughout this entire story, potentially connecting confinement to even larger unsolved mysteries in physics, including how gravity itself might someday unite with the other fundamental forces explored earlier in this journey. For now, this question remains genuinely open, sitting at the absolute edge of human understanding. Every single fact confirmed throughout this entire story, every experiment, every calculation, every extreme machine built specifically to study it, all point toward the exact same unmovable rule, confirmed without exception, yet still missing a final answer for why the universe demands it in the first place. Every quark inside your body right now sits locked in a partnership older than the sun, older than the Earth, older than any star currently burning anywhere in the visible sky. That partnership formed within the first few millionths of a second after the universe began, inside a scorching soup of free quarks and gluons, and it has never once broken since, holding steady through billions of years of cosmic history all the way to this exact moment, quietly persisting through the birth and death of countless stars along the way. This story started with a simple, almost impossible-sounding fact. Nobody has ever successfully pulled a single quark away from its partners and captured it alone. Every attempt, across every laboratory, every accelerator, and every experiment ever conducted, has ended the exact same way, with new matter bursting into existence out of raw energy rather than allowing a lone quark to ever escape. That single unbroken pattern connects everything explored throughout this journey, from the narrow, ever-tightening flux tube stretching between separating quarks, to the scorching quark-gluon plasma that briefly filled the infant universe, to the crushing, uncertain cores of neutron stars scattered somewhere in the darkness above you tonight. Each piece of this story reinforcing the exact same underlying rule. Confinement does more than simply describe a strange rule confirmed inside particle accelerators. It builds the very foundation supporting every atom in existence, generating nearly all of the mass found anywhere in ordinary matter through the trace anomaly, shaping the chemistry that allows stars to burn, planets to form, and living things to grow. Every element inside your body, every breath you take, every thought firing through your brain right now depends entirely on quarks staying locked together, forever, without exception, through a force so extreme it dwarfs gravity itself at the smallest possible scale. Scientists have pushed this rule to its absolute limits, building tunnels 17 miles long, cooling magnets colder than outer space, and running calculations on supercomputers powerful enough to simulate an entire proton one tiny piece at a time. Every single test, every simulation, and every extreme machine built specifically to challenge this rule has confirmed the exact same outcome, again and again, without a single exception ever recorded, across more than half a century of dedicated research spanning nearly every corner of the globe. A deeper question still waits, unanswered, underneath everything covered throughout this entire story. Nobody yet knows why the universe demands this particular rule, instead of some other possibility entirely. Why quarks must stay locked together rather than roaming freely the way electrons and photons do. That question remains open, sitting at the very edge of human understanding, waiting for a discovery nobody has made yet, perhaps inside a machine still being built, perhaps inside a calculation nobody has finished, perhaps inside the mind of someone watching this exact story unfold right now. The rule holding your body together tonight is the same rule that shaped the first instant of the universe itself, and it has never once failed. Somewhere out there, in a lab or a lecture hall or a bedroom staring up at the night sky, someone is about to ask the question that finally cracks it open, and when they do, the answer may reshape how humanity understands matter itself,